In 2004, Indonesia was shocked when a leading human rights activist, Munir Talib, died during a flight to Amsterdam. At first, people believed it was only an accident, but later, an investigation showed there was something much more serious. Today, we'll hear from a narrator and scientists who worked on this case to learn how science helped to find the truth. Munir Talib died on the flight to Amsterdam. At first, it was believed to be a natural cause, but a later autopsy revealed traces of arsenic in his system. Who did it, and how was the potion discovered? The answer is the science.
In 2004, a human rights activist died. The news was really shocking, but how was the truth revealed? The answer is analytical chemistry.
Analytical chemistry played a vital role. Using techniques like AAS, scientists can detect traces of heavy metal like arsenic in blood or tissue, even in very small amounts. Samples were taken from Munir's stomach and liver, processed and analyzed using spectrophotometer. The result clear: arsenic level far above safe limits.
The modern case is an example of how the science can solve cases. Without analytical chemistry, the truth could have remained buried. Analytical chemistry is not just about the labs, it's about defending humanity.
Let's go over the detail of collecting your UV visible spectrum. You are going to need a few things, including the sample you prepare for IR, your clean solvent from the IR experiment, an extra beaker for waste, some cuvettes where your TA will supply, and CHAMS wipes. Let's start by setting up the experiment on the computer. We'll go to workstation computer and the scan program, which is right on the desktop. Once you got the program open, we'll need to set up the experiment to be sure that we're collecting across the proper wavelengths for this particular lab. So go over to the desktop tab and confirm that you are going from 800 nanometers to 400 nanometers, so that we'll only be looking at the visible spectrum. You may also want to change from surface to phase. That tends to give a better spectrum, and set your baseline so that you can collect a baseline, and the software will then subtract and give you a better result. Next, you need to prepare a blank. Because we are using baseline correction, we'll need a blank. So we're going to use pure solvent, then show the instrument what that solvent looks like and have the subtract from our spectrum. We'll begin by rinsing on the quartz cuvettes using your blank solution. Be careful when you do this because you don't want to stretch the quartz cuvettes, and the gas pipette unable to do this if you press too hard against them. Once you've rinsed off a bit, take a jam wipe and whip the clear side of the cuvettes to be sure that there are no smudge on the outside could adversely affect your experiment. Next, we are going to add the blank solution to the clean cuvettes. You want that solution to be at least 2/3 the height of the cuvette to be sure that the light beams that being used for analysis in going through your actual solvent and not the air in the headspace above it. So this should be plainly right here. Now, with this blank prepared, we are ready to do our baseline so that the instrument comes to strike it later from our result. Let's blank the instrument now using that blank that we created. We'll set the compartment cover back, placing the cuvette containing our blank solution into the holder. Now notice that the clear transparent sides are pointed left to right and that's the ground translucent side are front to back. At this point, we are ready to blank the instrument, so we'll go down the baseline and click OK. The sample is now running an experiment of 10 solvent and determining exactly what the transmissions of that solvents and then setting in 100%. Now we will remove the blank and we are ready to empty our cuvettes, reload our new test solution and get our spectrum. So let's prepare our sample so that we can collect a spectrum. To prepare the sample, we'll take our cuvette and of course pour out the blank solution. Next, I'm going to add just a drop of to the solution in the IR experiment. This is because don't want to sample to be nearly and concentrated for this. Once I've done that, I'm then going to take my clean pipette and use it to add more of my assigned solvent. This will dilate the sample so that it's not too dark, so dark that the experiment in the UV won't work. So I add a little bit solvent here, making sure the spirit and bit so that it's nice and well mixed. And notice when in hold this up, a white canary that you can see is only very slightly colored. Now let's collect our spectrum using the sample that we create. Of course, to begin we need to open the cover and place the sample in the UV spectrometer with the transparent side facing left to right. Then we close the cover and go to software, where we'll begin that experiment by clicking on the start button. If you are the first student of the day, you'll be prompted to give a file name. This name will store at the data for the entire lab session, so be sure that you give it an appropriate name. Next, you will be asked to label your sample with a name that you can identify as your own. After clicking OK, the experiment will begin. And you are able by identifying our sample from the instrument and closing to here cover to be sure that this doesn't accumulate inside the compartment. So I can see the next, I'm going to dump the sample into waste paper and going to give it several times using that because I'm not using the canvas from the experiment. Finally, it's that when I do this, I'm very careful not to let the pipette touch against the walls of the cuvettes and potentially touch them. After about 3 liquid have been added and dumped out, the cuvette can be considered clean. We'll wipe down the outside to make sure there are no smudge for the next person who uses this cuvette. We are done cleaning up and we are now ready to hand the instrument off to the next student. Based on forensic finding report by Tempo magazine, Muni's stomach contained an arsenic concentration of 460 mg per liter, far exceeding the typical contamination level found in seafood, which averaged around 22 mg per liter. The lethal dose of arsenic is estimated between 46 to 76 mg, meaning the amount detected was several times the fatal threshold. His heart blood show arsenic level 31 times higher, contained 4.8 mg per liter of arsenic, significantly above the usual level of less than 0.3 mg per liter in the general population. Moreover, the urine volume found in his bladder was less than 15 cc, indicating severe dehydration. Additional, compared to the normal range of 250 to 400 cc, Additional signs include a greenish stomach content and feces resembling water stools, both classic indicator of acute arsenic poisoning. No trace of alcohol or common sedative were detected in his blood.
Analytical chemistry is not just about numbers and formula. It's about the truth, justice, and the future. Because science can speak when people cannot speak up anymore.